PyTorch of last year, which is the sort of different programming model for like orchestrating large clusters in a sort of single controller manner. This is like very convenient for things like async reinforcement learning, which is why we have Colin, who's one of the Monarch core developers, and then Alan, who basically used a lot of the work in Monarch to build a post-training library. We're going to talk about like their journey, like building this out and why it's interesting. So if you're interested in like low-level systems, modern RL libraries, I think you'll really enjoy this talk. So yeah, without further ado, Colin, Alan, please take it from here.
Yeah, thank you so much, Mark. It's great to be here. So first of all, if you guys are able to see this, and Mark, if you can provide a link, that'd be awesome. We have a interactive tutorial thing, which we put together. Mostly Alan deserves most of the credit. Thank you, Alan, for doing this. So you can clone the repo, UV sync to get all the dependencies, and actually run. We're using this notebook called Marimo to run some of these pieces. So we're going to do a mixture of running things live and going over the notebook and going to some of the documentation today. So yeah, feel free to do that while we're talking, and you'll probably catch up to us when we're actually ready to run stuff. And just a brief overview of today. So yeah, I'm Colin. Nice to meet you, a core developer on the Monarch team. I'm going to be doing part 1, which is all about Monarch. What's the motivation for it? What's the history of the project? And some of the use cases, in particular, developer experience, fault tolerance, and what we call the distributed tensor engine or tensor compute engine that Monarch provides. And then Alan's going to go all over asynchronous RL and the details of that and how Monarch can help that. And finally, time permitting, we're going to go into a deeper dive into how Monarch is actually built. Internally, it's a pretty cool project technically, in my opinion. So we're going to go into the code base and documentation and talk about that. But this first sort of parts are more on like the user application side. So yeah, and feel free to let Mark know if there's questions. We can take them live. But yeah, let's get started. So this is the first notebook, kind of talking about the history and vision, if you want to follow along. And I have it run. This is actually running it. So the motivation for Monarch initially was about fault tolerance at scale. So if you might have seen or heard about some of the interruptions, unexpected delays, or lack of goodput, as it's sometimes known in the industry, with large-scale pre-training runs. So these are some of the numbers from the Llama 3 pre-training run. It's running roughly at 16K GPU scale, and we're hitting a mean time to failure of roughly 3 hours. And this is due to a variety of issues. It can come from GPUs, it can come from networking, bugs. So basically, at this scale, your mean time to failure gets to the point it makes sense to not always do the default, which is a costly full restart of the entire training job, restoring from checkpoint. All of that time that the GPUs are not spent doing meaningful compute is wasted compute. So Monarch was built with this in mind, really initially about fault tolerance in the regime of large-scale tensor compute. In particular, Monarch was built around designing and ensuring correctness of fault-tolerant programs, as well as how to handle and roll back when you do find an error. So we'll go more into that, especially in the fault tolerance section, but that's a certain, definitely an important context for Monarch and why it exists in the first place. In this initial notebook, we're going to talk about why Monarch exists, a little bit about the tensor engine or distributed tensor compute and what that means and what it is, how the Monarch that was presented at PyTorch conference shifted into more of a general actor model with the tensor engine built on top of it, what that means and why it's important for distributed machine learning. We're going to actually run a Monarch program, talk about some of the details, and talk about message passing. One very useful framing for Monarch is Monarch does distributed fault-tolerant message passing and why that is so important. So let's jump in. What is the tensor engine? The tensor engine allows for distributed tensor compute, where you have one program distributing the program to individual workers who will actually be executing this. And importantly, this is done asynchronously. So you can asynchronously distribute compute and only request the results when you need them. This type of program is this type of programming model is called single controller. So there are other examples of single controller you might have heard. One I know in the industry that is a very also cool piece of technology is Google's Pathways. The Ray from Anyscale is also another example of programming design in single controller, and it has a bunch of advantages. Important to note, this is contrasting with what most people are familiar with, which is known as SPMD, or single program multiple data. In the SP regime, you canonically have a single train script, a train.py, and every single rank runs the exact same program from start to finish. Typically, there is actually communication and coordination that happens, and this is done pre-built into the program, often through collectives, whether that's with Nickel, for example, from NVIDIA, but collective communications. You can do barriers to synchronize. You can distribute tensor compute, all reduce gradients, right, in like a DDP parallel, distributed data parallel regime. And then if you need to do some other coordination, you have to basically build that in. So for example, if you need to make decisions about how to resolve past failures, you need some sort of distributed consensus protocol that's baked into your SPMD program, which can get complex and hard to debug. So all of that is, Monarch is a single controller programming engine, and the tensor engine is doing it in a distributed tensor compute fashion. So let's go into a little bit more detail about this. We have this controller or client script, which is authored in Python. Here, we're going to introduce the concept of a device mesh. This is very similar to the concept in JAX, for example.
Colin, I apologize. Like we're getting some questions in chat about. So like, could you possibly zoom in more on the content, because I think there's like a decent amount of white space.
Is this better?
Maybe more.
Sure.
And then I'll just put your face on the left-hand side. So we can do this, and I think we should be good.
Yeah. So I'll try to zoom in. Thank you. And also, again, you can also look it on your own if it's hard to see. Feel free to follow along. Does this look better to folks? Or I can zoom in more if you want.
It does look better, yes.
Great. So yeah, we're talking about device mesh. So this is similar to the concept of a device mesh in JAX, or the device mesh in PyTorch distributed device mesh, which is typically used alongside dtensor for what's often known as a global SPMD regime. But in this device mesh, we have a abstraction of a mesh of devices. Typically, and in Monarch's case, absolutely, these dimensions are labeled. So one of the pitfalls, the painful pieces about authoring, especially local SPMD code, is that every single SPMD script has to keep track of who you are and how you're acting in your ND parallel dimension. So of course, these parallelisms include data parallel, which can include FSDP, tensor parallel, expert parallel, context parallelism. These types of parallelisms are naturally expressed inside as dimensions of the device mesh. And Monarch is built with meshes everywhere. We construct a mesh of hosts to make up the sort of available compute we will have. We have a mesh of devices here, which represent typically a GPU. An accelerator is a device. We have a mesh of actors. We have a mesh of processes. We have a fine-grained process, control outside of just multiprocessing. So everything is a mesh. So here, conceptually, we construct this mesh, which represents 4 hosts, 8 GPUs, and the 2 dimensions are data parallel and tensor parallel dimensions. Then what we can do is we can activate this device mesh. So any PyTorch tensor compute operations done in this context manager will be doing tensor compute operations, which again will be fully asynchronous. So for example, we can take X, which is presumably a tensor that lives on this mesh, and we can pass it through the model to get the loss, and it will compute all these tensors on the device mesh. We can do loss.backward. This is actually Monarch-specific code where we take the grad, which is a tensor that the controller is aware of, has a reference to, and actually is materialized on all the devices, and we can run a reduce operation. So the single controller is instructing all the devices in this mesh to participate in this reduction operation along the data parallel dimension and using the average reduction up. And of course, we can actually run the optimizer with optimizer.step. So this looks very similar to native torch programming with the exception of this reduce. And essentially what is happening is the single controller program, which does not have the materialized tensors, but is aware of them, is going to distribute this tensor compute. And yeah, so that's basically. So this is, you can imagine how this might make it easier and more natural to orchestrate hundreds, thousands, tens of thousands, hundreds of thousands of GPUs. And it is a different model fundamentally, that SPMD. And go ahead.
And so Colin, so these APIs are like higher level than torch distributed, like as in like grad reduce is not calling the torch distributed API, which is under the hood calling nickel.
Yeah, good question.
So like, and maybe same question for device mesh. Like my understanding is like this is like a different concept of mesh than the detensor mesh, even though they look similar. But yeah, I was wondering if you could speak a bit more to those.
Yeah, good question. So this is a different API than dist.allReduce. Yes. However, actually implementation-wise, it is using the majority of the PyTorch distributed implementation under the hood. We actually have our own, for example, C10D process group. We do instantiate nickel communicators. We have these wrapped up in actors. We're going to talk about it later. Everything's an actor, but we have like a cum actor, a nickel actor, and this nickel actor will be calling nickel reduce under the hood. But yeah, it's a different API. And importantly, as we'll talk about, especially on the fault tolerance side, there's benefits to orchestrating these on a sim controller because we have a full view of the program.
All right, we have our first question from chat and by Garrett, which is there any advantage to the asynchrony in this example since the reduce needs to be synchronous anyways?
So yeah, good question. So there's actually one thing that's conceptually important to keep in mind is traditional we're thinking about synchrony and things like what workers can do in relationship with each other or with regards to the host and device, right, that have their own conceptual compute streams. Here we're talking about asynchrony in terms of controller issuing instructions to the worker. So this is like for example, similar to a host to device or device to host sync point, we can introduce forcefully controller to worker sync points. So when I'm talking about asynchronously here, I'm referring to that. So what I mean by that is we are never waiting explicitly on any of the tensors on the controller. So all of these will be we're not doing anything fancy in terms of PyTorch on the hosted device or how these ranks coordinate with each other, but we are fully asynchronous with respect to the controller and to the workers.
Got it. Okay.
So hopefully that makes sense. I know it's confusing because it's different than some of the ways we think about it. But again, we want fine-grained control of. It's similar to async IO in Python, right? To the async await model, where we will have futures and we only await on them. The controller, it's more than just futures because, well, it is futures, but we have this, and we'll get into in detail in the tensor engine. We actually have like a data-dependent engine where if there's a failure, we will cancel future work. And on the controller side, we actually have implemented with fake tensor a full record of all the tensors that exist, even though we don't actually know what they are yet. We just know that they exist. We have a promise of future tensors. Yeah. So yeah, it's hopefully it'll be more clear in distributed tensors, but feel free to ask questions now or later. So one thing to keep in mind, this was the initial vision and goal when we created the Monarch project a year and a half ago at this point, a little bit over, was about tensor compute. And what we have done is we realized that the majority of the primitives and technologies we built to handle this type of use case is actually more general. And there's also use cases and reasons why you don't want to always have to be at this very lower level granular tensor compute level. You might want to think about this async IO general compute on actors. You can author your own actors, for example, in Python. So Monarch and the Monarch to actor module, which you can see in the majority of the examples we have, is actually not focused on the tensor compute engine and focused on this more generic piece. And there's a lot of reasons and discussions about you can mix and match these two different models. And when you might want to do one, which I would love to get into. I mean, I think I'll talk about a little on the fault tolerance section, but we're going to switch to this more generic that's not necessarily where the controller has a reference to all the tensors, but we have a reference to arbitrary compute. And this is known as the actor model. So yes, let's talk about the actor model. So we will go in much more detail in the very end, but in a very short preview, the way that Monarch works for the control plane layer, which is everything we've been describing, we have a system called Hyperactor, which is built in Rust. And we use the Rust crate Tokyo, which is asynchronous runtime. That is, we use to basically create ports and channels to communicate between all actors. We have MP, SC, multiple producer, single consumer queues for all of these actors to guarantee in-order message passaging. So we built all this for the tensor engine. And what we realized is that we could use it for the actor model. Yeah, and just as a brief technical preview, basically what we do is we take arbitrary Python work. We use like async IO coroutines. We can serialize this work and then run this work not on the async IO runtime, but on Tokyo's runtime, on this asynchronous Rust distributed runtime. So that is the preview of what we're doing. So let's talk about the programming model though on actor model. Like I said, we're going to move all of this to Python. Monarch lets you define your own actors, and we communicate via messages. So an actor it's useful to think about an actor as a stateful, compute that maybe Ray has if you're familiar with the Ray programming model. But individual actors are described in an actor mesh. They have their own state. They communicate to other actors by sending and receiving messages. And everything in Monarch, including implementation as well as encouraged user code, is often thought about this inheritance model, this tree of actors. So you can imagine, we're going to go into an example of like how you might want to use this. This is sort of motivated by the asynchronous RL use case, which Alan's going to give a very deep dive into. But for now, we're just going to think about two separate actors, which are a trainer and a generator. In this case, a trainer is a canonical, you can think about an SPMD trainer, think Torch Titan or Megatron or whatever, that wants to optimize its optimize the model, and the generators are wanting to generate rollouts in the async RL process and might get updated by the trainers later. But these are the two sort of components which are separate in our system. We're going to talk about this host later, but for now, host is a way to get what we call a host mesh. And what we're going to do is we're going to spawn procs or Unix processes on top of this host. So now we have a host mesh. We're going to spawn spawn these procs onto them to get a proc mesh. So in this example, we have two proc meshes. We have the trainer procs, which has one dimension called GPUs and has one process. And we have the generator procs, which we have 4 processes. So we have these two different abstractions, one that is going to be running the trainer actors and one that's going to be running the generator actors. So after we have their proc mesh, we spawn the actors on top of it. So we spawn trainer on trainer actors and generators as you'd expect. Now we have a reference in our single controller program to the mesh of trainer actors, as well as we have a reference to the mesh of generator actors. And now we can do things like tell them to do things and communicate with each other. So we're going to have like a very simple synchronous training loop here where we're going to iterate. We are going to get on the mesh of generators. We're going to call what we call an endpoint, we'll talk about later, called generate. This is similar to an RPC. And we're going to use this adverb or this instruction to how to do the messaging called call. So this will issue instructions to the entire generator mesh to call them with the prompts that we want them. And get is our synchronous API for making this distributed compute blocking effectively. So once we call get, we will wait on the result of that, and we will get a result back from all of the compute that the generators are generating. Then we're going to correspondingly pass them into the trainers. So the trainer actor, which again is a mesh, in this case, it's a single process mesh, a single actor mesh on a single process, is going to do its train step. It's going to use this different adverb. And then remember, train step is this RPC-like endpoint. it's going to call one because we only have one of them, and it's going to pass in the samples, which are these materialized work that we brought over to the client script via the synchronous API. We're waiting on this feature, and we're also calling get to make it synchronous. So this is, hopefully this makes sense, but this is the way you use actors, what they are, what they represent. We have this host mesh, we have a proc mesh, we spawn actors on top of it, and then we can coordinate between actors using this message sending, everything where we printed at. So now let's go into actually run some code. So now hopefully you can follow along here. And I have started this Marimo notebook separately, which is running in this tab. So you should be able to run this if we scroll all the way down. This is our first ping pong example. You can also reference in our examples in our documentation. But let's run this code. So it's pretty fast. We're using actors, we're using endpoint, which I kind of talked about is like an RPC, and some information about the rank, who we are, as well as this host. So first, in the actor model, we subclass actor to define your own arbitrary actors. Here, we have an actor which is going to be pinging other actors. That's their job. We define the initialization. We have given a name based on its rank in the mesh, effectively on this GPU dimension.
Colin, you might want to zoom in a little bit again.
Oh, yes, thank you.
Which actually maybe is a good segue into questions here. Maybe let's zoom in more. Like I think just like zoom in unreasonably. So yes, this is better.
Okay.
Because like there's a lot of white space I think on the left and right. Yeah, I mean, like so maybe this is going to be a very newbie question, but you talked about how this is not an SPMD model, but hey, like I see an if condition on the rank. Like what's going on here exactly?
Yeah, so we allow you to, so in this case, yeah, it's similar to rank, and we're more formal about what a rank means because we organize all of these things into a mesh. So yeah, so you can use what we call rank because many of our users are familiar with this terminology. It doesn't mean you can't use information on rank and split. In fact, like that's often what you want to do. So yes, we use this terminology of rank. It's basically a way that when you're in an individual actor context to know where I am in the current. So this current rank is implemented through something called a Monarch context, which contains your shape and extent. We'll talk about them later, what the difference is, and where you are within that. Yeah.
And I wonder if you could go to the past code snippet that you had, the one that had the one with the training loop where you did the generate stuff. I just want to ask a question.
Yes.
Here, yes. So basically here, if you don't call .get, you would error on the next call, or like, because like presumably here, so you're explicitly saying when to synchronize data versus like, yeah, because like ultimately, like, so generate.call is a will return a future.
Yes.
Get forces a synchronization.
Yes. Yeah. So
and you need, yeah.
This would be like a promise effectively. So I don't think the promise has values implemented. So you'd fail when you try to get the values of this future. What sample mesh is what we call a value mesh, which is like a mesh of values and allows you to iterate and do things on them. So yeah, if you didn't have .get, it would error here.
Oh, okay. Yeah, keep going. Thank you.
Mm-hmm. But yeah, and I think just to bring it back home to an earlier question, again, it's useful to think about controller to worker sync points, right? This is introducing that point. This is explicitly waiting. But if you didn't need to do the compute yet, you would not probably have this await yet. And so we'll talk a little about in the distributed default tolerance stuff, how you can use this to your advantage. So yeah, cool. So I think we're talking, we have our own act. This is a different type of actor. It has its own init with its own information, and it has one endpoint. You can think of endpoint, like I mentioned, like an RPC. And it defines what type of, how do you want to call your actor to do things? So we have a single endpoint here called ping, where we are going to ping with a message. And so this is our actor definition. So similar before, we're going to get our host, which is a host mesh, and it's a one-dimension host mesh. It's just this host we're running on. We're going to spawn procs onto it. Here we're spawning two processes, and we are spawning the ping pong actor onto both of these procs. Now we're going to do something different where we're slicing this mesh. So this is very similar to mesh slicing in other contexts, but we're slicing this actor mesh ref of actors along the GPU dimension of 0. So we're getting the 0th actor mesh ref and calling this the ping actor and pong actor. Now, at the end of this, these will both be their own actor mesh references, but each will only contain one actor in this case. And then we're going to just simply iterate, and we're going to tell the ping actor mesh ref to ping. And again, we're using this add one call verb and waiting for it. So we're going to get the response, and then we're going to do the same thing on the pong actor. We're going to tell it to ping. Yeah. So you can see, and then at the end, I think we talked about the results. This is a value mesh, and we're going to iterate through this value mesh and the results to items and just display. So you can see that we ping pong these actors back and forth. Yeah. So this, not a very interesting program, but hopefully illustrates what you can do, or like some basic actor mechanics. Any questions before we move on to scalable messaging?
Yeah, so maybe you touch on this a bit more, but like so far to me, this reminds me quite a bit of the Ray tutorials. So I was like wondering if you could speak to like, yeah, why do we need yet another system that's like it for PyTorch?
Yeah, great question. So like I mentioned, the actor model is, I think, useful conceptually to think about Ray. It is very similar. In Ray, you also can have stateful or stateless arbitrary Python compute that you can put. I think there's some differences. For example, Monarch gives you finer grained control about, you can spawn multiple actors in the same process. For example, so there are some key differences. One of them, I think we talked about already, is the tensor engine, right? Monarch was built fundamentally to be tensor native. So one way to think about is sort of a more tensor native Ray, both in the tensor engine, as well as we're going to get to later on, Alan's going to get to on the data plane, the RDMA layer. And another big difference.
So what does tensor native mean exactly?
Tensor native means in the tensor engine, for example, we have on the client script or the controller, we have references to all of the tensors, and we're distributing tensor compute. So what we actually are running on the client script, we are ref counting all the tensors. We are constructing a fake tensor graph of all the tensor compute that we're expecting to do. You know, like before we showed you can have a model. We all of the model that runs on the controller will have a, you know, tree of fake tensors on it, and like the inputs of out and outputs of every single tensor up on it. And these will not be materialized on the client, and these exist on the worker. By tensor native, like we have a full ref counted references to every tensor that's being orchestrated in the device mesh. That is one of the dimensions of talking about with tensor native. And there's a lot of cool stuff you can do when you use this. The other one is on the data plane side, which I also think is more tensor native, where everything in Monarch, we have references to actors. And typically similar to Ray, right? Like you might not always want to materialize this, but we have references, and these are in the actor or the mesh abstraction to buffers, like tensor parameters that live on one actor, and we can use them by another actor. So a canonical example.
It's like that's like RDMA, so things for
Exactly.
like weight sync, right? Yeah, I see.
Under the hood, we're using RDMA as the transport to actually do this, but conceptually it's very similar. Right? RDMA, the program model is meant to feel like you have a remote access to a device that actually is not owned by your process. It's very similar idea. And so you have a buffer into a tensor that's not owned by you that uses like RDMA mechanics under the hood for transport. So these are two examples of what I mean by tensor native. And I think one third benefit that Monarch has, and we're going to talk more in detail in a little bit, but it's built to scale to very large scales from the very beginning, and it has a very principled fault tolerant strategy around our hierarchy of actors and supervision trees, which we'll talk about.
I also wanted to add in one more point that Colin's actually about to talk to, which is the support, like native support for like gangs. And so everything in like Monarch is like mesh based. You saw some of it in like the D-tensor mesh stuff. But I think that like one unique thing about Monarch is that it's like designed around being mesh centric through the design. And so I think Colin's literally about to talk to that like right here.
Yeah, so maybe one last question from chat then, which is like, are there any serialization constraints on endpoint arguments, if any?
Yeah, good question. Yeah, so what we are using, the serialization we talked about, we are using Cloud Pickle here. So Monarch today is not doing anything magic in terms of making sure that, like, if it's Cloud Pickable, we have similar environments on both the client and the workers. Things will work, but if it's Cloud Pickle is going to fail, Monarch will fail.
But Cloud Pickles, if I recall, it's like it can pickle processes too, right? It's like fairly, right?
I am not sure. We have certainly not tested anything like that, but I know that you can run into weirdness when your environments like cannot speak to the serialization format that Cloud Pickle is using, and we have no specific like answers for that as of yet. I mean, it's also come up in our internal problem set.
Yeah, per Gemini, it seems like yes, it can actually pickle processes. Okay, cool. Anyway, we'll get to that later.
Yeah, I think that is something useful to mention, like the Monarch actor model. Under the hood, we are using, you're defining your own coroutines. We are going to use Cloud Pickle to serialize the work that you want to do. And then we are going to place these onto the actor like channels and ports, which under the hood is using the Tokyo's asynchronous runtime. So that is a useful way to think about what is happening from a technical perspective about limitations. So yeah.
Okay, we can keep going then.
Mm-hmm. Yep. Okay. Yes. Now I want to talk about scalable messaging. This is one of the, I think, benefits Monarch has is about how it was designed with scale in mind from the ground up. So what do I mean by scalable messaging? Again, we're talking about this messaging that's done this like hyperactor, like control flow layer right now primarily, but everything is O of log n. So as n, which is the number of processes, increases, you can canonically think about maybe one process per accelerator, for example. So maybe 8 or whatever, 2 processes per host, depending on your setup. These will scale logarithmically. So this is basically both directions. When we do what we call a call or a broadcast, we're sending out the message to every single actor in the mesh. This will be O of log n, and we do that for tree-based routing. And the same happens on the other side when we do what we call reduction or aggregation. When you're expecting a response from all these actors, we will reduce these values using a run length encoding, and we will do the reverse message passing, also using a tree-based routing mechanism. So there's a cool diagram here, which we presented at PTC that I cannot get to render correctly, but here we are. I'll zoom in. I know this is small. So what do I mean by that? You have your client script, right? Like the client script issuing, who owns all these actors, initially the root client. We're set like, this is sort of like a factor of 4 based routing, where if we want to broadcast a message or use the call adverb message to all these actors, we will not do a point-to-point communication between the client and every actor. Instead, we will use Monarch's own internal routing to make this more efficient, which results in less messaging, faster, and also doesn't bottleneck the client, right? We don't want the client to be responsible for all of this. And on the inverse side, when we are expecting the response back, we use a run length encoding. Typically, the responses are all having some, they're not maximum entropy. There's some encoding we can use to compress them, and we respond it back. So this is one of the important things keep in mind, which again, really only comes to play if we're talking about tens of thousands of processes, in comparison to Ray, for example, but it is something we've designed from the ground up in Monarch. And also I should mention, you can implement things like a barrier, for example, and of course we looked at an all reduce, even if you're not using the tensor engine on top of this, and I think you can imagine how you might do this. And another piece is we also enable more sort of fine-grained messaging. We do this by exposing the Rust. We have a PyO3 API with underlying Rust level about what we call channels and ports. So ports, we provide a port for sending and a port receiver for receiving messages back. And a channel is the actual underlying channel transport that communicates with actors. We support, for example, like TCP. We support Unix sockets. So we support a few different types of channels. And basically, under the hood, we all implement this with send, which you can use, again, in Python if you want to expose your own piece. But all the adverbs we talked about are actually implemented on top of send. So you don't have to like worry about the ports. These are typically patterns you might want to do. But if you wanted to, you could basically use send directly and manually call receive on the port that you can also pass as a argument from actors. So we talked about adverbs a little bit, but the canonical ones, or like the typical ones that we use, are call, where we send to everyone in this mesh we're calling to, and we wait for a response back. We can stream, where we might be sending a message to this mesh of actors, and we want to string the results back rather than wait for all of them to be there. We might want to take action one at a time. Broadcast is, as it sounds, like kind of a fire and forget adverb where you're not waiting for any response back. And another one we saw earlier was called call one, where we expect there only be one actor. We haven't implemented yet, I believe, but we have plans for like a load balanced where you just want one to choose, basically one of the actors in the mesh. So there's different adverbs you can implement on top of the scheme.
So under the hood, send here just uses nvshmem, presumably?
No, so nvshmem, it does not. So this is all, nvshmem is typically for GPU data plane communication. This is using, typically for cross-host, this is using TCP. We also implement Unix domain sockets and some zero copy stuff for within the same process. So this is using the front-end network, not the back-end network, for these types of messages. And the underlying transport protocol will be chosen based on where the actors actually live in memory. So for example, like if you're, obviously TCP is what's typically used, cross-host, and then, does that make sense?
But then within a host, you would make different, like this is what you mean? Like basically you're like, where is this other host? Is this other host on my same node?
Yeah, so Monarch is aware. So if you, for example, spawn two actors in the same process, right? Then you can do a zero copy communication between the actors between this. So it's very fast. If you have within a host and you want to do you want to use between two processes, we use Unix domain sockets for that communication. And then if you're two actors communicating across hosts, we will use TCP for this front-end networking. And then the data plane nvshmem style Q-pair communication comes up when we want to use on the data plane. So this is actually separate communication stuff in Monarch. Alan's going to talk to more about it. But you can imagine whether you're sending tensors or even other objects that you really want the backend network very fast, high bandwidth communication, you can do this as well. But it is separate from the front end sort of hyperactive communication we're talking about. And in particular, you have to, there's guarantees we're going to get, for example, about message ordering. You want to make sure that you use the control plane messaging to guarantee message ordering and use the backend data plane communication for actually doing this high bandwidth transport. The biggest examples we have are the async RL trainer to generator communication sync. And we have some fancy stuff about actually sending out like worker environments and code changes that. So actually, that is one confusion we hear a lot, Mark. Actually, it's because we offer both this control plane and data plane, it's easy to get them confused. These are actually completely separate mechanisms where the RDMA is our focus on the data plane side. Everything control plane, none of it's using GPU backend network communication.
Yeah, I guess like as you're talking, like the way I was thinking about it is like, hey, if you're transferring tensors, then yes, like basically, but if you're transferring like messages or functions or processes, then probably no, right? And that is that correct, by the way?
Yeah, exactly. Like it's
okay.
all based on more control flow. It's like a traditional
Yeah.
infrastructure separating your control flow from your data flow.
Yeah.
One data
But it's basically like what kind of message are you sending, and then where is your peer? Basically, these two things
Yeah,
determine
what type of
how
message
big
you're
the peer is.
sending. Like in terms of orchestration, is it important that these are sent in order? You know, to maximize
Oh, I see.
your good put, like doing work, or the correctness of your algorithm. I would say that in general, use control flow, control plane messages unless high bandwidth is very important for you. I think a rule of thumb is 40 megabytes, right? Like if it's bigger than 40 megabytes, you might want to think about using the data plane. We actually have an RFC to maybe automate this to make it easier on users, but it's not implemented yet right now. Users choose it. And most of what we're talking about is on the control plane side, and most of the data plane stuff we're talking about, Alan's going to talk about later.
All right, I think we can keep going then.
Yeah, so one other piece that Monarch guarantees is on message ordering. So this is important. And basically what it means is that if actor A sends a message M0 to actor B, then later sends M1, actor B will always receive N0 before M1. And when actors are handling the messages they receive, we always handle their messages sequentially. So this is important to guarantee correctness because it's like an asynchronous runtime that's very distributed. This is the guarantee that you have around message ordering. So yeah, most of the time you'll want to like have a single actor. If ordering matters, you want to have a single actor orchestrate that, or use some other mechanism to coordinate between message, like actually handling and executing the RPC, or executing the endpoint. So, okay, I know we are longer than I was expecting to be here. This is the first one of, I think, 8 we have in mind. But just to summarize, Monarch is thought about, we have the tensor engine, we have this lower level or more general framework that's more similar to Ray, called the Monarch actor model. It's all built on top of a multidimensional mesh of actors, mesh of hosts, mesh of processes. We have a strict fault tolerance and supervision tree lexioms, which we follow. And we enable point-to-point low-level RDMA, which uses the data plane, not the uses the backend network, not the front-end network. And we have built-in distributed tensors. The 3 big use cases that we have explored building in Monarch, although you could use Monarch for other components, are fault tolerance, we've talked about. So fault tolerance algorithms, especially in distributed ML training. Interactive developer experience, typically also the ML training we're going to talk about next, as well as asynchronous RL is a very powerful one. And Alan's going to talk about that later. So yes, hopefully this makes sense. If there's any questions, happy to take them, or I can jump to the next notebook. We're going to talk about interactive developer experience.
Yes, maybe more of a logistical thing. I think this is awesome, but like I think at our current pace, this talk is set to be 5.5 hours long. Like because it took us 40 minutes to go through the first chapter. So here's like my suggestion. Like I think considering there's a lot of good questions, let's sort of aim for like a 2-hour talk, and then I can always invite you guys to do the second half. And I think we'll just maybe start a bit earlier in the day so we have time to go through the 3 hours. Hopefully that's okay, and that doesn't put too much of a dent in your work. So if you just like to continue linearly or pick a best of, I'll leave that totally up to you guys. Hopefully that's okay.
Yeah, that's fine with me. And what I will do is I will go a little bit quicker over some of these, and I'll pause for questions, and we'll let the crowdsourcing decide about interest.
Yeah, I think I'm not helping with the interruptions. I guess, I'll ask, like, I see another question from T-Kong, which is, are there any performance penalties when enforcing message ordering? Is that controllable if I don't need strict order?
Not really. So at the end of the day, we're still going to dispatch. Monarch always assumes that we will dispatch messages by dispatch, like we're going to execute on the RPCs, if you will, in the order they're received. So if you don't enforce message ordering, so I guess the question is, do you not care about the order of messages, or do you not care about, do you want some sort of different, multi-process threaded work inside of your actors? I would assume it's more the latter. And Monarch is not prescriptive about this at all. Like, so for example, you could your actor can construct its own thread pool and execute arbitrary parallelisms you want it to do. You can use inside of an actor mechanisms like async IO, event loops for orchestration or whatever you want. And you could basically build actors that their whole job is just to like have work, queue it up, and manage this yourself. We actually do some of these techniques in some of our fault tolerance. So yeah, but so I hope, I would assume but I guess that's only one of the ways that I can imagine it matters. It is true that we have like a multiple producer, single consumer queue that enforces message ordering from the same actor. And that's fundamental. And it's also true that the actor, like the thread it's actually executing messages, is serial based on this queue. And if you want more parallelisms, you got to implement yourself, which is totally fine and valid.
Yeah, it is brain breaking a bit, like when you like imagine sort of like this multi-layer of asyncness. Like I'd be curious if any sort of reasonable human could program like this. I guess have you seen any so far?
Yeah, well, so I think I think we should, maybe it's more useful if we get examples, right? So I think there's like the tensor compute layer, right, where you're actually doing this, and we actually have a way to do separate streams per actor, which is very similar and implemented with CUDA streams, right? So this is one of the layers you might want to do this. Another one is the sort of fault tolerance use case, in which, and I can talk more about that, where most of the control flow that's happening on Monarch is actually like much higher, much larger granularity. And then within that actor, you might want to be doing, has its own, like you can spawn your own checkpointer, you can do a bunch of different things to coordinate where you are. But I think the question I would ask, and then there's the async RL, right, where we're talking, even there's a lot of parallelisms happening inside of VLM, we're not orchestrating everything that's happening inside of VLM, for example, from Monarch. We're saying, hey, generate your rollouts, because that's the important control flow. So I would question, if you're limited, if this feels limiting, is the control flow of a single programming model right for that use case? And hopefully giving a sense, or some of the use cases we found it useful, gives you a sense of the type of granularity where it didn't feel that we were being limited from a performance perspective by this type of model.
Yeah, like basically there's some situations where the black box is fine, basically. Like, and this sort of seems to be what you're hinting at.
Yeah. I think, so here's my philosophical take, right? Like, especially if we're thinking about from a programming model perspective, a single controller programming versus SPMD programming. If it is useful to reason about the algorithm you want to express, where there is a single control plane, then it might be a good candidate for pushing this to the single controller programming model. If it's adding no value whatsoever, meaning it's equivalently easy to implement your algorithm by just like all the ranks are doing the same thing, then there's not really a lot of value to having a centralized controller control plane, right? With some exceptions, right? But that is a good framework to use. So for example, I know we're skipping ahead a little bit on the fault tolerance use case. You might take an example where, hey, my trainers are doing fine orchestrating in SPMD style, but I want to layer on fault tolerance of like, hey, someone fails, what's the policy to do? This type of algorithm, like, hey, having a policy, distributed consensus of who's alive, what attempt do I want to do? This you can express and just embed this inside of an SPMD program, but it might be more painful. And putting this to a single controller allows you to like algorithmically reason about it, execute your policy, and distribute the control flow. And because your granularity of your steps in this case is like, do a step, for this attempt with this all reduced quorum, it's not limiting, like the trainer is not blocked on like waiting for those control flow messages. You're not limited by like the bandwidth of the control flow to these. So that, in that case, but I'm sure you can think of examples where you are limited by this like MPSC queue and the single runtime. But if that's the case, then just, you do multi-threading, or you can spawn as many processes you want on this host, right? Like if multiprocessing is the right solution, you can imagine spawning processes if you want them to be supervised by Monarch. If you don't care about the underlying parallelisms being monitored and aware of Monarch's control plane, just put them entirely opaque to Monarch. because you can do whatever you want.
Yeah, it's a good heuristic. Like embarrassingly parallel problems, for example, aren't like a good fit for a single controller because you're like, it's embarrassingly parallel. It's fine. So
We're
like
not
that's right.
creating, tensor cores from
Yeah,
models.
I see. Yeah. Okay, wonderful. I think we should keep going then.
Sure. Okay. So yes, let's go. So I'm going to go to the next notebook, and let me go ahead and actually get this ready to run. So, okay, great. And click here. Cool. So, okay, here we go. One of the use cases we've seen is interactive DevX. Now imagine you don't even care about single controller, right? You are running into this problem where you're past the point where you can develop on a single host, and you need to develop parallelisms or something and debug your training run on multiple hosts, which have multiple processes. And imagine that your typical flow you might be using, and again, yours in the SPMD regime doing a pre-training job. Let's say you're using Slurm, so you're using like SBatch to send the job. Every time, like your iterative loop is like you send a training job, you get, the cluster gives you machines. Hopefully it's not hours, but it might take like, tens of seconds to minutes to get the machine. The machine has to like start up provision, maybe run some health checks. Then you like see the results, check out the logs. This is sort of like your loop. This might be slower than you want, especially like, let's imagine you're just doing some iterative development, but you can't test it out at a smaller scale. This type of problem, so one of the things we see is that like there's just a longer iteration loop, right? The time we're waiting to queue from the machines from Slurm are longer than maybe even we need our training job to run. So one thing you can use Monarch to do is we can use Monarch. Oh, and sorry, actually a couple of other things. Interactive debugging, and basically every time we SBatch, we're like sending all of the, our full libraries, whatever, our user code over to all these machines. One thing that Monarch can allow you to do to solve this is essentially do like the allocation with the scheduling one time. And in this sense, what we're telling these hosts to do is run an event loop forever and wait for us to connect to you and create what we are constructing of a host mesh abstraction. So we have this host mesh ready, which again is this abstraction of a mesh of hosts. What Monarch can do very quickly is use Monarch's control plane to say, hey, host mesh, do stuff, right? Like spawn your processes, spawn your actors, even just run your training loop. Like your entire control flow is just initialize and run, right? This actually, number one, is much faster. So this is one thing we found, which we call like the SPMD interactive developer experience, is just in practice much faster and easier to do stuff. And secondly, there's some other advantages of how you can use Monarch for things like remote interactive debugging, like a distributed PDB debugger is a accurate way to think about it, as well as syncing your code, like your workspace code that you might, like let's say you edit your trained.py script to all of the hosts very quickly. So that is like the high level teaser about what interactive developer experience and what problem it's trying to solve. This is also, if some other folks have used programs like Ray to do this, right? If you're familiar with this. So let's just imagine we have an SPMD train script. We just want to use standard DDP. We have a vanilla train.py script. There's nothing super interesting or fancy here. We're constructing a small linear model. We have a little train loop to do things. Yeah, very, very straightforward. So what we can do is we can use this little helper tool, the module we have called SPMD Actor, which is designed for this type of use case, where we basically have actors where their entire job, it's like a one-to-one actor with a trainer, and their job is to run the SPMD train script. So here we can go into the actual code execution piece and run this. So this is using the same train.py script as before. Here we go. So we can see we're running. Let's talk about while Monarch is running what we're doing. So first, we're just instantiating this. We have this importing this actor. We're getting our train.py script. We're getting our local host and spawning process on this host. Let's imagine this is like using H100s. We have 8 of them, or A100s of 8 GPUs. We spawn the actor onto this proc mesh. We're doing some stuff just to construct or get the master address and master port. In this case, it's a trivial example because it's a localhost, but you can imagine it's fancier. This is one of this get host port is a helper kind of function in the SPMD module to get the master address and master port from the 0th host in this SPMD. And we're calling it. And then we are actually, now we have a master address and master port of what we want to use for our C10D rendezvous. And then we're calling effectively our main trained up high main function. SPMD actors has this function main that just calls the train script. In this case, we have no arguments, but you can pass them in. So here we can use Monarch to do exactly this. And you can see that we're using Monarch to basically call torch run inside of a host mesh. So this example is not super interesting, but I think it does represent the foundation for building the relatively straightforward but still useful application on top of Monarch, which is this interactive library experience. So now that we have this, and I'm happy to take questions. There's nothing interesting yet, but or I can go on to like how do we make this interactive. Any questions about what we're doing?
I don't know if it's super. Actually, let's see. I'll go with the chat question first. So TK Kong is asking, in Ray they have this by executables mechanism to allow users to control the binary or virtual env used for actor tasks. Is this something y'all support as well?
So make sure I understand the question. There's a virtual env.
Yeah, let me put it on the screen. Can you see it?
By executables mechanism to allow users to control. Yeah, we do not have anything like helper stuff like this. I don't know, Alan, if you've used Ray more than I have. If you,
I haven't seen this before, but I just looked it up very quickly. I think I see a follow-up comment, but it's basically like if I wanted to, for instance, start a Ray worker in a different Docker environment than like my original caller. Do we have something like that? I don't think we have that in Monarch, but Marius has talked a lot about like, oh, we can maybe spawn a proc in a particular Docker container. And I know there's some work that that actually is ongoing, designed for the async RL case, but probably could be used in this capacity. But I don't think we've done any advertisement of this yet because it's still being developed.
Yeah. So I think this type of stuff we are relatively nascent at. We have initial setup with Kubernetes through both our native Kubernetes job, which just came out a couple weeks ago with our 0.3 release. There's also some external contributors that we also have recently put. One is SkyPilot there. And we are exploring what this looks like in the open source ecosystem. We have not had a lot of utilities to help here, but hopefully it should be somewhat straightforward for us or external users either to contribute or to on themselves to add. I will say and I'm going to go into a little SPMD, what we have done internally so far is we've had a separation of, and this is using some of the TorchX tools, which some of you guys might be familiar with, where we actually use Conda to package the user's Conda environment. Then we also have a user's workspace. And so the flow is typically you one time send the Conda environment in which all of your user like worker code is running in, and we have an entry point to actually like do things like find it, activate it, all of that. So all the workers are Unix processes are spawned into this environment, and then we have the user workspace tools. We have some utilities to sync the kind of in the interactive code base, but keep it small enough so we don't have to sync everything all the time. So one of this is called Sync Workspace, which uses rsync under the hood, and there's some other fancier stuff that we're working on. But that's what we have so far. I don't think we have what you're asking about.
All right, I had another question, but maybe let me save it when you're done with this notebook.
Sure. Okay, so what we're talking about SPMD that we have that works in open source as well as internally on our own internal schedulers using the mechanisms I just sort of alluded to, is we have also a SPMD job. So we haven't talked about jobs yet, but jobs or the job trait abstraction, if you look at the Python code, are ways to represent work, like a conceptual job. Sometimes these jobs might be interactive, like we're seeing here, where we basically launch the job. We have a handle on the local client script to this job, and we can reconnect to it and do things. Or it can be like a one and done job, like a batch job. We have some support for both. But this is the abstraction that we are talking about. And this jobs typically has a reference to the mesh of hosts. Everything initially when you enter Monarch land is about a mesh of hosts, and then you have control over spawning processes, spawning actors onto it. So serve is a way that we introduced for this, like a way to make it easier for this common SPMD path to construct a job. What serve does is basically talk to the scheduler to get those resources. Here we're leveraging TorchX basically to do this for us, which supports Slurm and Kubernetes. Yeah, and then we are also caching like the work that we expect the SPMD job to do. Typically, this is sort of caching the resulting like torch run command or entry point and torch run command that TorchX produces under the hood, which is used a lot by users of PyTorch internally to Meta. So what this looks like is we import serve. We basically give it our train script, which will basically become our workspace effectively, like I talked about. And we are serving using this vanilla torch run command, or it can be a torchx command on the local CWD torchx scheduler when we run SPMD. What this does, and we can run this, although it's not super exciting. What this does is it's going to create a job. We are going to handle this job. This job has a cache to the resources, which in this case is not very interesting because it's all local, but it would have the Slurm resources we have access to, and then it's going to cache again like the instructions for how to run it. And now we have this handle, we can keep running SPMD as many times as we want. So this is the exact same flow as we have above, but now we've made it interactive, at least in the Slurm case. So like I was sort of teasing, we can call run SPMD again with the same handle, and it's very fast. Yeah. So I'm going to talk about why we might want to, how to make this remote, breakpoints and stuff. But any questions before I get into that?
I'm very excited about the debugger, so please keep going.
Cool, yeah. So yeah, this is basically what we do is we get a job. Since we cache it, we actually cache this in a serialized format that defaults to this .monarch job state.pickle file. So we can just like load it using the job trait definition and then run it again. So this means you can just like pick up the same resources as long as your schedule administrator is not going to kick you off of them. You can leave it running for however long you want and keep using them. And in practice, we found that this really cuts down on the actual day-to-day pain point of like this iterative development loop that people have when they go into this remote, running things remotely. So yes, and then we also provide, which I'm not going to go into too detail today, but I can talk about it, but I can't show right now. Monarch debugging. So effectively, what we have is a little tool which uses like some Netcat fancy stuff under the hood called Monarch Debug. If you run Monarch Debug from the same host that's executing your client script currently, what you can do, and you have a breakpoint anywhere in your user code, even if it's like an SPMD deep inside some remote function. What you can do is you can open up a debugging terminal, and basically it feels like you are doing distributed PDB debugging. So you can do things like, step into the chain. You can actually choose, do I want to select on a single process or a single actor, or you can actually cast messages to all of the actors using the same Monarch system. So for example, you could have 2 breakpoints and then cast all of your workers in the tensor parallel dimension to continue to the next breakpoint, for example. And then you would basically be able to, all of your remote workers would pause on the next breakpoint and wait for your client script debugger to control them. So yeah, we talked about that breakpoint Monarch debug. Unfortunately, this well, I'm not sure exactly why, honestly, this was not working, and nor do I have access to a Slurm cluster to try this. So I'm not going to show this live. But we do have a tutorial on this in the Monarch examples, which I'm hoping is working on a real Slurm cluster, but I have not verified. But if you do try it and it's breaking, leave us a GitHub issue. And this is, again, I'm not going to run this, but this is an example of what this looks like actually going into the multi-node regime using Slurm. So here, this is, again, using TorchX. This SPMD job is piggybacking on the TorchX extraction layer. TorchX has this idea of an app def, which has like all the roles you want to play, which an SPMD job is typically only one role, the role of the trainer. And you specify in the vanilla arguments that you expect, like how many nodes and procs for nodes, how you want to do rendezvous, your train script, your resources. This is all like TorchX stuff. If you're not familiar, you can look at the documentation. And then if you call serve with the scheduler and the TorchX scheduler configs, this will run. And it will give you the job, and you can like iteratively run SPMD on the job. So that's, yeah, I don't have any more to say. And then, well, I guess I can also talk about sync workspace, which is a little more complicated, and honestly something that we have a solution for more that's meta focused and this like conda on mast, conda on our internal scheduler, which is called mast. I know Meta's like published that before, environment, and we're still working on improved support with Kubernetes. And actually, this is an area that if you have interest in using Monarch or working on Monarch or contributing to Monarch, could be useful, because there's a lot of different types of setups, environments, ways of people doing things, and we welcome contributions here. Okay, well, I am not able to see any questions, so I'm going to move on, but feel free to ask questions about this later. I do want to cover two other things while we still have time. Oops. So one of them is the fault tolerance stuff. I think this is definitely a meaty subject that I want to cover more in detail. So we talked about how the motivation for Monarch initially was fault tolerance, particularly at these large scales, mostly in this sort of pre-training SPMD type environment, but it could be used anywhere. So there are three things I'm going to walk you through here. One is how Monarch handles errors, or we call supervision events, and you basically interact with these through vanilla Python try-catch blocks. This is sort of probably what most people need, even for our own applications, what we primarily use. I'm going to talk about what supervision trees are and what they mean. And also, this is a separate library PyTorch offers called TorchFT, which is implements some common strategies for fault tolerance in the SPMD regime. And then we took that and added Monarch to it to make the detections faster and automate the policies, basically. So this is sort of what we're going to talk about on the fault tolerance side. So, okay, Monarch has what we call a supervision tree. This is borrowed from Erlang, where the idea is that every single process and every single actor in the system, and under the hood, Monarch is implemented in a cascading series of actors we sort of hinted at, all has an owning actor. Everything has, and all the way up, the client script is your sort of ultimate owning actor. And the idea is that the owning actor, should expect to receive a supervision event if there is a failure in any of the actors it owns. Additionally, we provide some convenient stuff. So the caller of the actor, if the caller of an actor's endpoint, right, like the RPC, receives a failure, we also provide the caller with that information. Well, this is technically best effort, but it's in practice very useful. And often the caller and the owner are the same regardless, but from a strict standpoint, that's true. So this is what we call the supervision tree. This allows us to, for example, let's imagine we have an actor that is is going to raise an exception, and we want to be able to handle it. We can wrap this in a try-catch block, accept the exception, and choose how we want to handle this. Of course, like the underlying actor might be dead, but at least the system is able to make progress and decide what to do despite these failures. So I'm going to go ahead and launch this last notebook just so we can follow along. But this is exactly what we should be seeing. Great. Yeah. So you can see the actor did not say hello because it threw an error, and we did not make, and yeah, we cannot make more progress. So some more details about this. Errors will get routed to the caller, but we also might not need a response. So we talk about the broadcast adverb where we don't actually accept a response. So in this case, the supervision owner is still guaranteed to have knowledge of the failure, even if they're not actually accepting a response and there's no port for the for it to reply to. So this enables what we are calling finer grained supervision, and we do so via the dunder supervise method. So the dunder supervise semantics, such as that we get a failure, which is of the type mesh failure, and if you want to handle it, this is sort of like handling an exception and not further raising it, you return true. Otherwise, you return false, and you can have like the other actor, for example, handle it, even if you might want to take this. This is basically a way to like define a policy. So you can define that, like the owner of the actor, how do you want it how do you want it to handle failures that actors that it owns see these supervision events. One other note as well is that ultimately the client script, which is like the main client we've been talking about, is the ultimate root actor for the actors it creates. And if there is no sort of handling of this, then this root, this like mesh failure will get bubbled up all the way, and it will actually crash the client process. And if you don't want to handle fault tolerance, this is sort of what you kind of want and expect to happen. If you're telling your program to do something, it raises an exception, it will say, hey, like main process, something happened, something bad happened. So you'll be note about it, and it will sys it, but you can actually control this behavior through this unhandled fault hook. Like, what do you want to do if there's unhandled fault effectively?
So Colin, something that wasn't too clear to me. It seems like you're hinting that like on these supervision events, it's like the failing actors that are notifying their parents that they're failed.
Yeah. So the supervision tree is such that the owner of the actor is guaranteed to receive the event. It's not the failing actor that notifies that. Under the hood, there's a few different mechanisms to do this, including a heartbeat protocol to see like, is this underlying actor dead or something. But yes, that the semantics are that there's always a root actor, and that root actor is guaranteed to receive the supervision event one way or another, either through.
I see. So, but when you say guaranteed, it's not like someone else is guaranteed to send the event. If the root actor itself just has a heartbeat on its children, this falls under these semantics that you're describing, which is it's guaranteed to receive the supervision event, even if it's itself.
Yeah. Heartbeat is like one of the ways to do it. But yeah, there's other ways. Like it's typical that we have faster paths basically to not have to like wait for a timeout from the heartbeat. But yeah, that's one of the ways.
I see.
But I think importantly from a user perspective, the semantics are, you have to be aware of who's your root actor. If you want fancy stuff, you should implement your policy via supervise. The default policy is it will just bubble up the supervision tree. And also we do make this best effort endpoint caller, which doesn't have to be the same actor as the root actor, which also receives a supervision event.
So I'm just like trying to think through some examples. Like, let's say, for example, your children actor are different like data parallel processes. And the policy I'd like to have is if a data parallel worker fails, I'd just like to keep going. And I don't care about my numerics. Just keep going with fewer GPUs.
Exactly. So we're actually going to get the exact example
of
the T thing later on. This is a common type of thing. So basically, you might want to have a fault domain, right? And you express your fault domain. You have a policy of like what happens if there's a fault in this fault domain. how can I continue the overall job process despite a somewhat smaller fault domain than the overall job? Yeah, and data parallel is a good or a good and simple way to do this.
See, T-Kong is asking a slightly more complicated question, which is how does the supervision stuff work in the event of a node death, and you need to potentially reschedule the workload because the locality of the GPU matters, like need to stay on the same rack.
Oh, okay, yeah, good. Okay, so first of all, how's it in the node death? If there is like a node or host death, that's not the root client host, then the root client host will see the supervision event, can define a policy via done or done supervise, or via handling it from the endpoint call. And that's the supervision part of it. It's the basic notification of failure. I think the second part of the question is what do you want to do in response to that failure, which is in response to that failure, what do I do if I guess like, can I not restart the host, or I can't remember exactly what you were saying, but yeah. So
I think the question seems to be referring to localities. Maybe I'll expand on the question myself, which is like, let's say if you had, I don't know, an NVL 72 node go down, which is like very highly tensor parallel, but now you don't have another NVL 72 node. Now you need a completely different parallelism strategy and spin up like new nodes.
Monarch does not have any secret sauce for improving like the policy based on locality or whatever. It's up to the user to author the application with this in mind, right? So if you need to, for example, you have a hot spare and you want to put it in, but you can't just like insert it because the locality of the host that died is complete in a separate pod than your hot spare, and you need to like reshard or whatever. That is completely up to the user to implement that type of logic. What Monarch provides you from a tooling perspective is the detection of the failure. And in practice, we see this is actually much faster than other ways you detect, because the other way is like SPMD scriptal timeout, basically. So this is typically much faster. And the second thing it provides you is some tools around host meshes for how you might want to isolate the failure domain. But like if you had something special, you need to reprovision a new, completely new pod to preserve locality, or restore a bunch of workers from checkpoints, that's all expected on user. Monarch doesn't give you any magic.
Yeah, but concretely, I think the way I would imagine the scope to look like is it's basically like it's very tightly coupled to the scheduler, right? Which is like, what is the state of my cluster and the next, like the free nodes that I have available. And then it's also a function of the parallelism strategies you use for your job. And then, I mean, so I can imagine this is going to be quite difficult to program, by the way. If done really
it is very difficult. There's a bunch of trade-offs you have to make, like the complexity of the fault tolerance, like how many spares do you want? Are these hot, meaning are they like loaded, checkpoint ready? Are they following? You have to do the trade-off of like, if you have lots of hot spares, should they just participate in training in the first place? Can I still make meaningful progress despite non-ideal locality? Is it worthwhile to to like stop training, reprovision to exploit locality given the available machines?
I see, but I guess the alternative is like basically like an exhausted prod engineer who's like on call deciding these things on the spot, right? So at least here you encode these policies as code.
Well, so
we're still much more reasonable.
For the record, like Monarch has no policies of like predefined policies of what to do on failure, how to recharge your model or anything like that. Like that's not, but there are like the Torch FT actually does. Like this is where they actually have policies for how to define your fault domain.
I see.
Monarch is all about, again, detecting the supervision events, and then how do you author your policy, right? In a way that like you can write it. But I think fault tolerance is a good example of what I was describing of what is the type of logic you might want in your sim controller. If you don't have your sim controller, it's like frustrating, annoying to author this policy of what you might want to do. But it's actually really helpful to have a single controller that's going to talk to your scheduler, or orchestrate whatever health checks you want to do, or whatever you need to do. It's not like an auto fault tolerance policy. That's more in line with what a Torch FT tries to do, and we're going to get to that example later with some common strategies.
Yeah, that's cool though. Like I think before you mentioned this, like I always envisioned Torch FT more as a a library of fault-tolerant communication primitives, but what you're also sort of suggesting it's actually like a library of policies for dealing with fault tolerance at that higher level. Yeah.
I'm not an expert, but that's the parts of the code that I've poked around on. The example that we built is more on that lines. Yes.
I see. Okay, wonderful. Okay.
I think like the torch comm side is actually where you talk about some of these. Like,
I see. Okay. Yeah, like this is I think where it's been hard because like I think there's like a whole bunch of libraries. I'm trying to understand the boundary between them. But okay,
yes.
I think your explanation made sense.
Yeah. Cool. So let me at least run this, and then we'll talk about. I think next is the torch FT use case. But what I think this is actually useful to run because it shows you how to use like supervise. So okay, so we have a fragile worker, which is going to raise an exception, right? We have the subclass actor crash exception. We have a supervisor that's your own actor. And it's going to basically keep track of its own workers, which it's spawning, right? So now this supervisor is the root actor of these workers, not the client. We're using async IO events just to because these to do signaling effectively. And this is what we're talking about. When we're talking about supervise. You can see the signature here takes in a failure, returns a full. We want to return true here because we're saying we're going to handle this. And what we're basically going to do is we're just going to log that we've caught it, set this async IO event. We also have this separate endpoint. So this is like the policy effectively, right? That the supervisor will do inside this actor. This is the endpoint, the RPC to actually do the crash. We're going to say do work, which we expect to have a crash. And we're basically going to wait for this event. This is like, because these separate endpoints, right, are not going to be executing, like these are asynchronous runtime stuff. So we need to do async IO events to coordinate if we want something like this to happen. And then we just simply have a get failure log. So we're going to do the same type of strategy where we have this host. This is the actor mesh. We're going to spawn procs. We're going to one process for the supervisor, one for the child. And then the supervisor is going to spawn supervisor, which you remember, we're going to pass in the proc mesh, which again, because it just references, it's going to be the supervisor that actually spawns this process and becomes its root actor. And then we're just going to crash it. We're actually awaiting it, right? This is like an explicit await. And then we're going to get the failure log. So, and then we're just printing it out basically. So this is basically, you can see what we're doing. We catch the failure, we print it, we print out the log. I don't think there's anything super fancy what we're doing, but at least it's a way to see how you can define this supervised policy for anything custom. Whereas before we just try accept caller, but this is like the more formal, utilizing the more formal supervision tree effectively. Yeah, I think we talked about this. Oh yeah, supervision tree. I'm going to skip over this, but basically it's everything we talked about where you have this tree of supervisors. If there's a here that's owned by this, and this orchestrator can the trainer supervisor can actually handle it or bubble up to orchestrator. You can author your code like this with like nested try catches if you wanted. Yeah, but I want to skip over to the torch FT. I think is more interesting. So torch FT is more like what we talked about, right? Where we have different replicas. Each replica is its own. A cross replica is alongside the data parallel dimension, not the FSDP data parallel dimension, but the actual like all reduced data parallel dimension. And our strategy here is we want to, and this is all torch FT, not Monarch yet. Our strategy here is if a replica dies, meaning if any worker or like communication inside that worker, which was preventing communication or whatever, dies, the entire replica is our fault domain. And we are going to mark this replica as dead or failed or not reliable. And then there's other details about what do you do with that replica. Do you like swap in a hot spare, which is not implemented, but you could imagine implementing something like that, or do you reprovision an entirely new replica, whatever. So Torch FT isn't doing anything like that yet, but what it's doing is basically marking as failure, and it's allowing the other healthy replicas to make progress. Because this is the data parallel dimension, right? This is doing an all reduce to synchronize the gradients between the healthy replicas. So without Torch FT, right, what's going to happen is if you just used vanilla dis.allReduce here, you're going to hang. And like you can basically catch your own timeout and do whatever try to do a distributed consensus protocol to figure out who is alive. But basically, you're just going to hang. And typically, what most people do is like cancel their entire job and restart it and pay for the restore from checkpoint. It's a very long process. But what TorchFT allows you to do is like, let's imagine you have 4 replicas. You can still make progress with 3 out of the 4. So you can maintain what's often described as good put, like useful flops to do training despite this failure. There's some numerics changes, right? Because instead of you're having like a lower global batch size, so you have to modify how that works. But that is a solvable problem. So everything. Oh, and I should mention the way TorchFT works is they have what they call a lighthouse service, which is actually implemented in Rust and over gRPC to act as the orchestrator effectively of all the replicas, and its job is to basically tell the workers to continue to work, and its job is to do things like checkpoint recovery. So this all exists outside of Monarch, everything I just described, which is like a data parallel, replicas of fault domain. There's nothing about how do I like recover afterwards, only how do I keep making progress despite the fault, the failure so far. Are there any questions about the fault tolerance scheme we're describing so far?
Apologies if this sounds a bit like a crackpotty question, but like I think one thing I found interesting in what you described is like, well, the reason why people I think presumably stop the job in the first place is because they're like, oh, I don't know, it's like too complicated for me to understand like what the heck's going on, so let me just cancel everything and like restart. And you could certainly have like policies that you encode that are like basically good heuristics. Is this like an area where you think like, I don't know, you give Cloud Code access to like your Kubernetes CLI and you sort of expect basically to be like a good eval being how long can you keep a job going at scale? Like, I guess like how much of this do you think is like there's like some good algorithms that everyone should use versus like there's a lot of vibes that should be like encoded and people should try things out more?
So first of all, my recommendation is to start with something simple and like get that to work and make sure it works, and then see where the loss of efficiency comes in, right? So, and actually before we get that, unless you're training at larger scale, this probably will not add you anything. Like the question is the mean time to failure sufficiently small enough that like on average, the cost of completely restarting your job from checkpoint is enough to warrant this worrying about this. So that's like sort of. Yeah.
Is the issue that the startup time like scales linearly in number of like GPUs or something? Like, well, what's sort of like the technical limitation here?
Yeah, a lot of the startup time. So your startup, you have to reload from everything from checkpoint. You have to reload your model state, your data loader state, your optimizer state, all the different stateful pieces of your program and of your jobs need to be restarted. You have to worry about, like, I think earlier we were talking about locality, right? Typically, you have various strategies based on how you're sharding to make sure that the overall, MFU is optimized based on taking into account the locality of these different, like, if you're in the NVLink domain or you use like InfiniBand, how you're doing, overlapping all of your, computing. There's a lot of work you do to make sure that works optimally. But if you just like swap in, like one strategy, naive thing, you could say, hey, here's a good host which has good GPUs or whatever accelerators you're using, swap them in. Then you're going to, restore that naively, that you could just restore that from checkpoint, but the locality is going to be all messed up, and you're going to take a huge efficiency hit if it's even possible, to communicate. So what typically is canonically done, like before this type of strategy, is you do start from scratch, you restart from checkpoint. You might actually physically swap in, or I don't know, whatever, in terms of like if there actually is a true non-recoverable hardware failure that you cannot do, you'll have to figure out, like, isolate that bad host and you restore from checkpoint. And this can take, yes, meaningful amount of time, minutes to restart everything, all of your state from checkpoint. And that's
Yeah,
and what's often, like, again, in the industry, I think that this is measured by good put. It's what percentage of your total available flops that usually used for training is like actually doing useful flops, meaning it's like doing new communications that's so like when I said new communications, right? You might have actually already done the forward backward stuff, have useful gradients, but if you have to throw all that work away because you have to go back to a prior training step because one of your other ranks failed, that's no longer useful work.
Right. Yeah, that makes it clear. Thank you.
So anyways, there's lots of strategies you could do. This is a very simple one, which in practice, I think is a good starting point. And only it's worth thinking about if your mean time to failure and your cost of restoring from checkpoint, which is like the very dumb thing to do, the very naive, I shouldn't say dumb thing to do, is worth this. And the framework to think about optimizing is optimizing for good put.
I see, but it's interesting because there's a clear formula, right? Like basically, if you measure the amount of time between two successive checkpoints and look at the number of GPUs, you could literally measure like the cost of that failure, which is like, it's like me going back in that much in time means this many GPUs, this much time, this much watt, this was the dollar value. So the cost of failure is quite clear, basically. And it's worse if you checkpoint presumably less frequently, and it's worse if you have a lot of GPUs. And then you're also saying it has like weird dynamics where like you can choose to checkpoint things quickly, rematerialize things quickly, but then you're not guaranteed to have a fast configuration. And so like, I see. Okay, that makes sense.
Yeah, and I mean, even outside of like all this fault tolerance stuff, imagine if you're just using all reduce, SPMD programming, you're having all of the ranks that have already like started and are waiting for this barrier for everyone to complete the all reduce. They're just sitting there, they're idle. So there's trade-offs in terms of like number of replicas and all these things. It's a ML space. I just wanted, again, I know this isn't the most advanced piece, but I think it's useful and instructive to talk about this like more data parallel fault tolerance strategy, because I think it's a reasonable starting place. One thing I kind of skipped over was the orchestrator's job in TorchFT is to do what's established quorum, right? So our quorum, which is like, which are the corresponding ranks in my quorum that I will be participating in the all reduce, that basically are aligned in all the other ND parallel dimensions except for the outer data parallel dimension with me, right? So this is like, there's going to be a corresponding rank 0, rank 0, rank 0 on the other dimensions and all of these. This job in TorchFT is through this Lighthouse service. So this is like the big picture strategy, which is useful to keep in mind. With that in mind, how can Monarch help, right? Well, Monarch can help in two ways. One, like this Lighthouse, this policy is actually very natural to express in a single controller. Really, this Lighthouse is acting as a single controller. And the program that it's orchestrating is basically, hey, do this training step with this quorum, right? That's its job, and to keep track of who's alive, who's dead, and how should the other replica, all the ranks on the other replicas continue if there's a failure. So this actually is pretty natural to express as a Monarch actor. And then the other thing that TorchFT is doing under the hood, if there's a failure, like TorchFT is not being notified that there's any failure. What it's going to do is it's going to say, well, I guess maybe it does its own sort of heartbeat. I can't actually remember, but primarily what's going to happen is all these replicas are going to time out, and that's how it's going to know, hey, like I cannot complete my all reduce because something failed. So what Monarch can add is two things. One, it can detect failures much faster. In practice, this is one thing we saw when we layered Monarch on top of TorchFT, was we were able to detect nodes faster. And two, you can express this sort of policy pretty naturally inside of Monarch of how you want to do upon failure. So I'm just going to go over briefly about some of the results of this, which we actually made a blog post about in PTC. You can read more about, but we trained a Qwen 32 billion model training. We injected faults. We ran on 30 node, 240 H100s on CoreWeave. So using Titan, right? PyTorch's pre-training library and TorchFT, injected failures, 3 minutes intervals, 100 total events. And we actually, just for fun, we put triggered different types of faults, from guild deadlock, host eviction, nickel abort, process killed seg faults. So compared to full Slurm restart, which is canonical baseline, we saw faster recovery speeds, recovery time, average recovery time, and everything. So I'm happy to take more questions on this. This was, again, like a somewhat straightforward replica, data parallel, fault tolerance strategy, how you can use Monarch to detect the failures, what you can top of them. There's a lot more you could do, and I'm happy to go into that to the extent that I can. But this is one of the main fault tolerance pieces. And just to recap, we talked about try except supervision trees, quorum-based training, Monarch and Torch FT. The next piece, which maybe for the sake of time I'm actually going to skip, is the tensor engine. The reason I'm going to skip, we already previewed that, and I want to give Alan more time. But are there any questions on fault tolerance before we go on?
I mean, I think I asked a lot of fault tolerance questions, so I think we could keep going.
Okay. So like I said, if we have time at the end, we'll go back to distributed tensors. I'm going to skip this. It's pretty cool. Check it out. Okay,
maybe I'll ask you one question here. Like SPMD seems fine for things like, data and tensor parallelism, but not so fine for pipeline parallelism.
Mhm.
So like presumably your pipeline parallelism implementations are like more readable than what you might expect to see in Torch Titan, which has like if conditions around the stages and things like that.
Yeah, that's a good question. Okay, are they more readable? So I think there's two ways to think about this. If you separate out pipeline parallelism, so yes, you can orchestrate. Pipeline parallelism fundamentally is not an SPMD control flow, which is one of the hard things I think PyTorch around like dtensor has tried to express this. It's difficult to do. So it is a natural candidate to put on single controller. I think one natural candidate to do is to put just the pipeline parallel pieces on single controller and to put the other SPMD parallelisms sort of as a done inside of what we call a remote function. They do have interplays, like there's optimizations around handling like the DI, DW split separately, which you need to take into account for FSDP interactions. But we have no public implementation of this. It is possible and natural, but all the stuff that the PyTorch team has done in our officially supported stuff is all in like not using single controller. I think that it's arguable about, I think I can see both ways about which is easier to read, because you do have, if you want to eke out efficiency, you do need to be careful about the relationship between the data parallel and the pipeline parallel interactions. And the question is really, is it also like, is it easier to read or author? And then is it worth, or what's the value of putting that in a single controller? I would argue that actually more of these fault tolerant orchestrations are more interesting, or like semi-synchronous training, right? Semi-synchronous training, you might have an inner outer optimizer done in SPMD fashion, or SPD plus pipeline parallel. And then you have, these are like what's known as like workers, for example, like local SUG styles. And then you have an outer optimizer being optimized on the controller. And then the single controller's job is to orchestrate these, make sure they don't drift too far apart. This, I think, is much more, it's definitely easier to read and to express on single controller, because you are back, if you do it in SPMD code, you're back to like this distributed consensus, forced into SPMD type of thing that's not natural to express. So yeah, TLDR, pipeline parallel, arguable, they do interact. So if you want to eke out efficiency, but fault tolerance, semi-synchronous training, this is much easier in my opinion on single controller.
All right. I guess, Ellen, should I start sharing your screen?
Yeah, that sounds good. Before we do that, I guess logistical question: how much time do you think we have, Mark, for the rest of today's session?
I think 20 minutes, unfortunately. So maybe you can give a teaser, and then the next talk could be more focused, I think, on RL in general.
Yeah,
that's okay.
That sounds good. I think I agree. Maybe we can like punt the async RL or RL specifics to another topic. But maybe what I can just do right now is like close the loop on some of the Monarch specific topics. Like we can go into like RDMA, try to go as deep as we can in the 20 minutes, and then we'll see where we land. Cool.
Thank you.
Okay. Yeah, that sounds good. Okay, let me just set the stage really quickly. I have another notebook here that like talks about like async RL and tries to set the stage for like why you might want to care about that and introduces all the components. But right now, I'm just going to like really focus on like one particular application within async RL. So at a quick high level, in async RL, I really like this type of problem space because I see this as like a pretty complex distributed systems challenge. You typically have what we call generators, which usually look like BLLM servers that like run on some host. You'd have some trainer, and then the main idea is like the generators will generate data that gets sent over to the trainer, and then the trainer will take the weights and then update it back to the generators. And so the reason why all of that is pretty interesting is because let's point out what the scale problem looks like. If we consider like Llama 3.170B is like a pretty big model size. We can use like a lot of back of envelope math to kind of calculate how big this is in terms of just like pure gigabytes. So like a 70B model might be like 140 gigabytes. And if we go to like a DeepSeek V3 style MOE model, that could be something like 1.3 terabytes of data. And so one of the interesting things is like you usually need to move these weights from trainers to generators regularly in these async RL workflows. And if you don't do this like effectively and you're doing this like in a naive way, then your async RL workload basically just becomes like a weight syncing workload. You can imagine this also applies to things like torch FT or disaggregated inference. Like this idea of like moving a lot of data from like one piece to another is like a thing that commonly comes up in like these really large scale distributed systems. So I just wanted to like start by demystifying this problem space a little bit more. So for weight sync specifically, there is one specific data path that I think we care about most. So from like a first principled perspective, you might have like a GPU dedicated for training, and you might have a GPU dedicated for generation. And so our goal here, in assuming that these GPUs are on different nodes, is taking this data from GPU A to GPU B, and they like cross over a network boundary. The way that this usually looks like is like I start from my trainer GPU, I go over PCIe to CPU, go again over PCIe to the NIC or the network interface card, which then gets transmitted over like a physical fabric over like an RDMA or remote direct memory access protocol, which goes over a NIC, back to PCIe, back to CPU, back to PCIe, and then finally populates the generator GPU. The bottleneck here is actually this NIC, the RDMA part. Formatting is kind of broken, but main idea is that like this actually goes over another separate network. And so if we like zoomed in a little bit more on what this kind of looks like, you'd have a node A, you'd have a node B. And so there's like different memory bandwidth tiers when we just talk about like moving data around. If we think about like within one single host, you usually talk about this like idea of like an NVLink domain. And that's usually measured as like 900 gigabytes per second. And main idea is like if I have memory in any of these GPUs, I can go from A to B, and that'll always like, you can write it such that it goes over this NVLink domain. This RDMA pass that I talked about between hosts does this track all the way through here and makes its way over to the other GPU. And the reason why I want to point all this out is that it is helpful to think about the fact that there are different memory domains and different bandwidths. And if you're like developing pretty complex systems, I think one of the things that I found was like pretty lacking, but the ecosystem has evolved for a lot recently is having the ability to take advantage of those links and make it feel pretty ergonomic. These numbers here, caveat, are all just from like what was published for Llama 3 using H100s. A few things that are also worth mentioning is that right here, I'm showing like 2 different NICs, but like in practice, this might actually be like 8 NICs, like 1 per GPU. And so you'd have like an aggregate bandwidth of 400 gigabytes per second. So if you can like fully saturate that, then that's, much more effective than just like the 50. Cool. And so just if we did some like quick back of envelope math again for like talking about like how do you do this like sync from A to B, let's consider again like this DeepSeek V3. If we assume that it is like 1.34 terabytes using bfloat 16, then one interesting thing is like obviously you can't fit all of that into one single GPU. And so if you are if your data center is connected in a way where you have a fast path from GPU over to a specific NIC, if you have 8 NICs and 8 GPUs, then ideally each GPU has its own dedicated NIC that is optimal for it, right? And so it doesn't really work out like that in practice, but my whole point is it's not really the 50 gigabytes per second. You're not just shoving everything through one single NIC. You have your data spread through multiple GPUs, and you have a really large aggregate bandwidth that you can then dedicate to like sending from node A to node B. And so, again, this is like a very rough approximation, but if you assume that we have like 8 nodes for a DeepSeek V3, you would be splitting like 160 gigabytes per node. Across 16 nodes, obviously 80 gigabytes per node. And so what you can do is take advantage of like this aggregate bandwidth and like transfer data from like trainer to generator in like under a second. And so this is a very ambitious estimate. I don't know that anyone's actually seeing this in practice, but it's just an interesting thought experiment that like in an async RL setup that you could use RDMA to transfer data very quickly. When if you just looked at the numbers from a bare like perspective, you might get scared of that. Cool. And so main takeaway here is it can be a little complex, but what we find is like RDMA is a really good way to make async RL practical at large scales. So to continue on, one thing is if you ever do any like distributed training, most likely you're already taking advantage of RDMA. The way that most people are able to take advantage of RDMA is through collectives. And so a lot of this is like written in Nickel, NVIDIA's collective communication library. And then above that, we have like nice abstractions through PyTorch distributed. And so one way of expressing this is just through process groups. So I'd create like a group or a world of things that I know want to communicate to each other. And then through very well-known collectives, then I can do this type of transfer in a very efficient way. This is really good and really effective for like the pre-training synchronous RL or synchronous workloads. But for async RL, it actually has like a slightly different usage pattern, which kind of breaks the world a little bit. So to set the stage a little bit, maybe I'll go through this quickly, but the reason why we might want async RL in the first place is because we presumably have multiple generators to maximize our generation throughput. And if we were to use Nickel to use that as our transmission from our trainer to generator, then what we have to do is like wait for everything to be in the same state, barriered, to finally then do like an all gather of all the weights. And so if you have like a straggler, like let's say generator 1 just takes a really long time to generate, then generator 0, 1, 2, everything else that has already completed is just waiting for our straggler to complete, our train step to happen, and then for us to like do the actual full transmission. And so one idea is like, what if you could actually just send the data directly to the receiver's memory without ever having to coordinate? And so the way this might look like is in like Nickel world is two-sided, like a send receive. The sender says, I have data, receiver acknowledges, okay, I'm ready to receive the data, and then you actually do the transfer. This is what I call like two-sided communication. RDMA actually gives you the ability to do one-side communication, which means I can just tell the sender, hey, like write the data directly to the receiver's memory. What's really cool about this is that the trainer doesn't actually need to know in this situation, like when the generator pulls weights. It can actually be fully, truly async. And so RDMA here is not necessarily like a faster TCP. It does bypass the kernel entirely. And what this technology allows you is to like directly read read data from registered memory and take advantage of our high bandwidth interconnect.
Alan,
And so,
Alan, just 2 questions. So the first one is like, if you could scroll up just a tiny bit.
Yeah.
So I don't know, back down. Like I think with the one where you're showing the slow generator.
Oh.
Yeah. So like presumably like another solution here might be you just take whatever's available and you just like use those and then you just like sort of drop everything else. Is this like very bad for RL people or is that like fine?
Okay. So essentially if we're saying like we have
So let's say we have n
yeah.
generators. One generator is slow. We just ignore it, and we just keep going with the other generations.
Okay, yeah. So if one's really slow, then what we could do is like cancel the fact that that's continuously generating, and then just like use the other ones, like down the total straggling time.
Yeah.
I think that's like definitely a thing that's possible, and it's probably the most practical solution today, just because like it's actually pretty straightforward to implement that, right? I think from like a theoretical like. If I think of like good put and like good usage of the GPUs, then I think it's like I think it works, but then it's like, okay, you could do a little bit better than that, right? And maybe that's the perspective I'd take. But then there's also another part of like, let's say you are trying to train multiple tasks, right? Like I might be doing something that's trying to learn math, but at the same time trying to do really long horizon coding tasks. Because if I use that heuristic of like I'm always going to drop like the really long coding tasks, that should never be good at coding, right?
Yeah, okay, that makes sense. Okay, another interesting thing you mentioned is like skipping the kernel. What does that mean? Could you speak more to that?
Yeah. So I guess like for typical like networks like TCP, for instance, a lot of this has to do with like low level operating system. I'm sorry, I'm not gonna have the most accurate technical terms, but all I know is that like typically what you would have to do is like take like a big chunk of data, like split it up into tiny pieces and then like send them over the wire and like in those chunks. And so that takes a lot of CPU cycles to actually process the full transfer, which is why like it could take a long time for you to do like a large amount of data over TCP can just be like a long time because of the way the
Oh, I see.
transport mechanism is implemented, right? Versus RDMA is just like, here's this giant thing, now just go like send it and the hardware itself will handle it. And then you have no more CPU cycles burnt doing that.
Well, interesting. I don't know much about Nix then. Like I presumably they're running their own kernel basically that like I don't know much about the like how those things run. So maybe I'll think of someone maybe from NVIDIA who could help us out.
In addition to skipping the kernel, like the OS kernel, I think they like the RDMA can also skip. It doesn't have to go through an SM, right?
Yes. Okay. Yeah. So Tikong is asking, do you see any benefit of one-sided RDMA if we do in-flight weight updates where we're okay with Frankenstein rollouts?
I guess there's two ways to think about this. And so here's my understanding of my recollection of in-flight weight updates. I think there's like two ways I can think about this. And okay, so the first way I'm thinking about is like literally that when the trainer's done, one-sided push trainer just goes all like to all generators broadcast and the generators don't even know that it's happening. I feel like that might actually work a little bit as long as the generation doesn't like just like get demolished as that happens. So if you want like pure efficiency and less coordination that you require, then like that could be useful. But again, my fear is like, let's say like I'm mid generation of one and then like something breaks. Or you're updating it as it's like doing a forward pass, which is probably what happens. Like I'd fear that you like just do very mathematically incorrect things. Maybe the other part is like what we did in Forge is actually like paused all the generations and then sent the weights over RDMA, and so we're not like getting the full benefit of the one-sided puts and gets. But I think like the way that I imagine the one-sided puts and gets working best is if we were to cut to the chase of like what this notebook is about, is like implementing a circular buffer where the trainer itself, once it's done with the train step, it can just like write to one slot in CPU memory. And then the generators, whenever they're ready to like pull, they just like grab the latest, transmit over RDMA, and then continue on. That's like the architecture that I like the most. So the other implementation of in-flight updates, which I think is what it looks like, is, for instance, if you're running generation and you could say like generate 10 steps, and then whenever I want to check if there is a new weight update, then I will just pull and then continue with the generations, then that could be useful. But overall, it's the mechanism of generator decides when it updates versus everybody has to agree when they update.
Got it. Okay. That makes a lot of sense.
Yeah.
Yes.
Cool. I mean, we have about 3 minutes left. There is like a separate notebook here.
You should finish your notebook. It's fine.
Okay. Yeah. I mean, for this particular piece, I think, yeah, the last thing I want to talk about is like just the APIs I can use in Monarch just to take advantage of RDMA. So Monarch implements something called RDMA buffer. And so if we went down and like went really deep into like how RDMA buffer is implemented, what we find is that actually to represent any remote data actually through the lowest level layer called IB verbs, you actually only need a really tiny handle that just talks about like, here's where my data lives. And typically what that looks like is like the address, the remote key, and the size. And Monarch wraps all this in something called an RDMA buffer. We're calling this like a magic pointer because it's really small. And so like if you were to run this this cell, what you would see is that like if we like scale the tensor size from like 1 kilobyte to like 10 megabytes, you see that the handle size itself like never changes because it's like this tiny pointer, right? And so if you remember and recall that Monarch is implemented in a way where we're really trying to optimize for scalable communication and messages, but that's all over TCP. One nice thing about this like magic pointer thing is that like now I can just like send this anywhere in my Monarch world, and then as long as two actors on two different machines know that they like can actually do communication physically over RDMA, then you can actually like start the initialization process and then actually trigger the communication from one end to another. And that's kind of what that looks like here. So what that kind of looks like in practice is I might have an example here really quickly. I might have a sender implementation, like a sender actor here that has its own set of data. And I put like an RDMA buffer that wraps that data. I can get that handle from any other actor. And then in this case, what I'm saying is like I have a receiver on the other hand that will actually take this RDMA buffer and then call this read into API, which will overwrite its own version of data. And so in practice, I can create like two processes, a sender receiver, send the data from the sender to the receiver, and then finally like do the pull data. And what I do here is just like do a checksum to see that they're the same, and they are in fact the same. And so what's like pretty powerful here is like there's like a lot of reasons why Monarch is uniquely a really good fit for like representing RDMA. Maybe we can get into that later, but main idea here is like it's really cool now that you can actually take advantage of really fast interconnects without having to like go through collectives all the time for that. Yeah, that's the main point here. And we've finally built a lot of really cool stuff from this insight, like the circular buffers, implementing a library called Torch Store on top of that. And all of this is like what we ended up using in Torch. But maybe we'll have to save more of this detailed information for next time. Mark, are you still around? I think that does cover the maybe the quick high level part. Yeah.
I will say it's okay. I mean, if there's sort of points you'd like to make, please make them. I really didn't mean to rush you. So I was just like, I was waiting for you to finish your thoughts.
Oh, okay. Okay. Yeah. No, I think that's like a pretty natural starting point. Maybe in the comments, if anyone has any questions about RDMA, happy to take them. But we can also like do like a deeper dive of it. But that might also be like a good, like effective reading assignment. Either one I'm fine with.
Yeah, I mean, thank you, by the way. Like, for what it's worth, I will post again a link to your like tutorial series. So please check it out, folks. I guess I see one question in chat, which is like, do you have any plans to support non-NVIDIA hardware? And do you foresee any new sort of unexpected challenges from doing so?
Yeah.
Colin, yeah.
Yeah, so we do. So EFA is currently in development. EFA, Elastic Fabric Adapter, is what is used on AWS. This is one of the big ones. So Monarch is released in 6 weeks increments, roughly, like meaning a new minor version. So I expect roughly 6 weeks time frame. Don't quote me on that, but or don't hold me to that, I should say. But yes, certainly soon EFA. We are exploring other types of NICs. Unfortunately, right now it basically is NIC by NIC. We're definitely going to add NVLink. We're actually a public roadmap, by the way. I think we talked about some of this that Chris Gottschalk put out. We talk about EFA, NVLink domain, which is actually slightly easier. And we are also working with AMD to make it easier to run on AMD GPUs, and we'll see about what types of NICs we end up supporting in that way on Monarch. But right now, the implementation that exists is like the CPU and the over Mellanox, InfiniBand, NVIDIA NICs. Those are the two that the library currently supports.
So, Colin, the roadmap you referred to is the distributed infra one that.
Yes, distributed infra. I think it's part of there. Yeah, you should.
I found it. Let me post it.
I think we've talked about all of this in the roadmap on the RDMA side.
Let me see. I think, is there anything in distributed? No, distributed is different. Okay. Well, thank you, folks, and apologies again, Alan, for rushing you in the end. I really enjoyed it. So like, I think if y'all are ever interested in coming back and talking a bit more, like doing a deeper dive on RL as sort of a domain, I think like a lot of things might click. But yeah, Colin, thank you for the wonderful introduction. And thank you for humoring me with my.
Of course, sorry, Alan, for taking all your time. But yeah, feel free to reach out on GitHub issues or PyTorch Slack or the Discord. You know, the GPU mode Discord. Happy to take more questions.
I guess maybe I'll ask since we're on this topic, like where are you mostly looking for contributors? Like I think you mentioned briefly having different schedulers, for instance, be better battle tested. Is there anything else that comes up?
Yeah, that's a great question. I think the two ways we've seen the most so far have been resource stuff like images, launching jobs. How do we sync resources? This is probably the biggest one. I mentioned the SkyPilot made an external contributor. We've been talking to GKE, then the other one is also on the RDMA stuff, especially some of the, like AMD is interested in making sure we can run Monarch better on AMD, including RDMA. So that's one of the areas. So I think these are the two of the areas I think are very useful in the sense of expanding the set. I think on the DevX side, I think it's actually interesting because a lot of Monarchs has been more with like meta style use case in mind, which is not always how other users are thinking about launching clusters. So this is an area where I think there's a lot of primitives that we offer and stuff you could build, but we're kind of scratching the surface. So that's also where I mentioned that one. And then, another one I should mention, I know Alan kind of didn't have time to talk too much about the async RL, but we have been in discussions with some of the different async RL libraries about like, is it useful to use Monarch for their coordination here? There's less of Monarch library integration, but like Monarch adoption, I guess.
It's interesting. So like just like finding creative ways of breaking and using Monarch would be like one of the best ways of getting.
Yeah, I think that. I mean, I think, even talk about, I would love to see a actual public example of like a correctly done with, FSDP02, DIDW, optimized pipeline parallel on-single controller.
Oh yes.
Yeah, that would be a cool thing. But yeah, in terms of library contributions, yeah, I don't know. Nothing. It's a lot of like kind of services or extending it had mostly what we've been doing, so it's top of mind for me. But of course, open. If you see issues in what we're doing, I think another actually cool thing is on the telemetry side. We've been doing really want to make it easier to debug and understand these distributed programs, and that's one of the biggest things that we've been working on improving since PTC. So if like there's cool open telemetry tooling that you want to see us work with or interact with, that'd be another cool integration point in terms of like capturing and understanding the program.
Okay, wonderful. Well, again, thank you, Colin. Thank you, Alan. Really appreciate both of y'all's time, and hopefully I'll see you both again soon.
Yeah, thank you for having us.
Thank you.